Thank you for being here for the last talk of the day. I know everyone's tired. So I should say this is joint work with James Scicluna, who is the guy who's done really the hard implementation work and the hard experiments work, and who's not here today. Okay, so outline of the talk, well, talking a little bit about grammatical inference, and also it will be useful for me to sort of say I am not an NLP person. Explaining why we're interested in probabilistic context-free grammars and why that specific task is a difficult task, at least learning them. The algorithm we are proposing, called Comino, and the experiments, and probably time for a discussion because a number of things have arisen from this work. So about grammatical inference and the distributions themselves. Grammatical inference usually is about just learning a grammar or an automaton or something like that, some device that generates strings given information about language. So even if in this place everyone will think that this is clearly inside an NLP, I should point out that it's actually a task which is shared with a lot of communities in this moment. There's a lot of people who are having grammars out there to represent their data, or more importantly, finite state models. So I've given a list of things there. The natural language processing should be a sort of last but not least. Right? Obviously the place where things started, but at the same time not the unique place. That's what I just wanted to point out. So the task we're interested in here is clearly an NLP task, unsupervised parsing. We're given some raw text, and we want to build a model, a grammar from this raw text. There's a twist, which is we're going to try and do two things at the time. We want a model which at the same time can be used from language modeling, which we've seen something about. So I want to be able to have probabilities telling me things which will be used to disambiguate, for example. But I also want to have the structure right. So I want to hope to do the two things at the same time, get the right structure and get the right prediction model somewhere. So that's why, well, the thought to do that, the claim was, let's try probabilistic context-free grammars. Basically, there are tools that exist that have been studied in a number of fields, but not necessarily learned that much, at least not learned from raw text, not learned in an unsupervised way, not that much. So it's starting to be an interesting topic, but only, let's say, in a nice way recently, even if, thoughts about it rise already from the 60s. So I just reminded the PCFGs is rules with probabilities for rules, and right from the word go we can see problems arising, like for the example, the fact that you can have ambiguity, so you're going to have to do sums over products of the rules we're going to use, and if we're not very careful, the grammars can even not be consistent, meaning that the sum of all probabilities won't be equal to 1. So that sort of gives challenges to more theoretical-minded people. So the class of context-free grammars is a large class, and people trying to learn them have repeatedly, let's say, failed or had problems with them. So people have come out with other ideas of trying to say, well, perhaps we can reduce the class of grammars. Perhaps we can go for a sort of slightly easier class. And the idea behind this is to use congruential grammars. So the idea, the simple idea on this slide is that perhaps dog and cat are substitutable from each other, one with each other. Meaning that every sentence where we use dog, we can use cat, and every sentence where we use cat, we can use dog. I mean, I'm not claiming this is true. I'm saying this is the idea behind being congruential. So just to get a little bit more mathematical, a branch of computational linguists have been working on something called distributional learning. So it's not distributions in the sense of probabilities, it's distributions in the sense of how these congruence classes organize themselves. So this is the only mathematical slide of the lot I'm going to be using. So we're going to say that for a given substring, we've got the global context that that substring may be using to the left and to the right. And then we're going to say, as in my cat and dog example, that two substrings or two strings U and V are going to be syntactically congruent, when they can be replaced one with the other in the language, which means that basically all the contexts of one are equal to all the contexts of the other. So that's just the generalizing what we said in the previous slide. And the context-free grammar is going to be congruential whenever the rules of the grammar somehow match these classes, meaning that everything that appears from a non-terminal, everything that can be derived from a non-terminal corresponds to one unique class or is inside one unique class. And we can go just a little bit further by making sure that that inclusion symbol becomes an equality, and we're going to say the context-free grammar is actually strongly congruential whenever, every time we've got a non-terminal somewhere, this non-terminal is actually giving exactly one class of the language. So a very strong condition, and we're going to have to see if experimentally it holds or not. But that's the sort of condition we're wanting to do. So this would be the case that is used without probabilities. If you're doing probabilities, you try and do the same thing. You're just going to say the dog, the probability of having context x, y with dog, right, is going to be equal to the probability of having context x, y, so x to the left and y to the right, with cat. Okay, so if we can measure these probabilities, which we're going to sort of probably measure by looking at the data, at the sample, to see if we've got roughly the same things to the left and to the right, then we're going to say that these things are substitutable one from the other. And then we're going to say, well, we're going to try and go for grammars which comply with the condition of being strongly contextual, which is a restrictive condition, but we're going to show that it's perhaps not that restrictive. So as I put out, there's a little complicated thing about this depending on cat, because the word cat may appear various times in the sentence, so we've just got to be very careful with these things. Okay, so that gives us the goal. The goal is to learn these grammars, and this is the algorithm. The algorithm is a three-step algorithm. So to get the general idea, the first step is to build the classes. So we're going to try and build as many classes as possible from our sample, from our data. So we're going to have far too many classes because every substring is possibly a class. So in this first step, we're actually going to merge some classes and decide that certain things look together because they are congruent. But we're going to still be left with far too many classes in there. So the second step consists in selecting a small amount of these classes. Actually, just the number of classes that we need to be able to rebuild a grammar which is going to generate our sample. So somehow, instead of having an overgeneral grammar which we wouldn't be able to put probabilities on, we're going to limit the grammar to a smallest possible grammar to do things. And that's going to be done using a solver. And then the third step is just very simple here, which is estimating the probabilities using a traditional, typical inside-outside algorithm. Okay, step one. Well, step one, from the sample, we build one non-terminal for every substring. So that means that then, for every substring, since it can be decomposed, I should have said that. We are going to use Chomsky normal forms, quadratic normal forms. So all rules just take two variables in the right-hand side. So that's why when I've got a substring like ABC, I will associate with ABC the non-terminal S sub ABC. And there are two possible rules, two possible ways of derivating this. ABC gives SA, then SBC, or SABC gives SAB, and then followed by SC. We can check for equivalence. So equivalence is going to be decided by a statistical test over the data to be able to see which one of these non-terminals, meaning substrings, actually share the same class, the same context. When we do this, there's going to be a cascade effect. You start merging things, and then other things get merged one after the other, just for sort of consistency of the whole process to happen. Okay, so yes, there's some sparsity here. However much data you have, you're not going to be able to have exactly the same context to the left and context to the right. So for practical reasons, we're actually going to have windows to look for K symbols to the left and K symbols to the right. But we could try other window systems to just be able to have more data to be able to make our comparisons over. So this is what happens if I take a sample AB, AABB, AAA, BBB. Obviously, this sample I am not running probabilities on, I'm just showing what's happening. So you build your congruence classes, where three of them are rather interesting between the congruence classes. The first one, A and B on their own, so class 1 and class 2, correspond to the terminal symbols. Each symbol is going to arrive separately because it's going to be usually used separately. The third class is going to be, well, the set of all strings. In this case, because they don't reappear in another way. So AB, AABB, AAA, BBB are going to all be merged into the same class. So, and then it follows in that way. So if you count, well, you're roughly going to obtain, or you could obtain, a squared number of congruence classes with comparison with the number, or with the length, the total length of the strings in the sample. Sample which can be a multi-sample if we are learning in the probabilistic setting. Okay, step two. So step two is well, let's say the tricky one. The tricky one is we've got far too many rules there, so people have tried using that sort of grammar. And since we've got too many rules, what we're going to do is we're going to try and find a sub-grammar from that grammar which still gives us the same language. So the trick here is we build one variable for each class we've seen before, and for each substring which appears in a class, we will build another rule which is actually going to go and give way to the different decompositions which it allows. So the base of the rule is here, but it's perhaps easier to understand through an example. I've got my congruence classes. I associate the Boolean formula that we have to the right. So one formula for each of the rules. And if I look the highlighted rules corresponding to non-terminal 6, what we can see there is that for AAB we have got one line of rules. Basically we're saying that if non-terminal 6 exists and is needed, then I'm going to also need either at the same time non-terminal 1 and terminal 3, or non-terminal 4 and non-terminal 2, corresponding to the two decompositions. We have the same. The other option is doing it through the 6. So 1, 2, and 3 as variables are going to necessarily be true. 1 and 2 because we actually need those the terminal symbols to appear somewhere in the grammar, and 3 because that's going to be the axiom, the first element of the grammar. So if we run a solver over this formula, and we decide that what we're wanting isn't just to satisfy, we want to find the minimum number of variables which satisfy that set of clauses, well, what's going to appear, what is going to be found here, is that x1, x2, x3, and x7 are going to be returned, and x1, x2, x3, x7, if we look at how they appear in the clauses, then they can be interpreted as the grammar which is in red down at the bottom, once we've made the adequate simple substitutions. Okay, so that's the algorithm. So the experiments, so we did two types of experiments. Some experiments on artificial data, and then we had to go at experiments on real data. Experimental data meant trying to find those typical constructs that you can find in context-free grammars and seeing how this type of methods was able to find them. So these are from typical textbooks. You can find palindromes, you can find ANBN, the Lukaczevich language. Also try to go for ambiguous grammars to see what would happen. If the grammar is ambiguous, once we've put probabilities on it, it's still going to remain ambiguous, and then things can become complicated also. So it doesn't mean that the Dick language is ambiguous. It just means that we've chosen an ambiguous grammar for that to see what would happen. And then there's some artificial NLP grammars. What does that mean? That over the years where people have tried to learn context-free grammars, they have built some artificial data sets and they've been trying to work on them. So we've just gone through the literature and found whatever people have been using. As you can notice, most of references are, well, a lot of these references are not recent. So then we said the task was to actually do prediction and to do structure. So for prediction, we chose Adios, which is probably the most likely candidate to do that. And for structure, a system called ABL by Menno van Zanen was used. And in each case, well, in one case we were using relative entropy, and the other case we were using micro precision, micro recall, and F1 score to be able to see how well we were doing. The data. So this data may sound disappointing. The goal here was to actually try and see if we could learn with very little data. So that's why on the artificial set, we haven't just filled it up with a lot of data. So we can find sizes of alphabet going from 2 to 50, and we can find number of non-terminals ranging from 3 to 45, run number of rules ranging from 4 to 80, and data sets from 10 to 100 strings. So this is how I'm going to just present rapidly the two comparisons. Comino against Adios. Well, Comino was obtaining better relative entropy in most of the cases. So to the left, you find the most artificial cases. To the right, you're going to find those probably a little bit more complex using natural language structures. And so, well, that's the sort of results we were obtaining. So I should say to the left, all the first half, Comino was actually finding the good grammar, the correct grammar. So from there onwards, getting good scores sounded correct. To the right, it wasn't necessarily finding the good grammar, sometimes because there wasn't a good grammar to be found. So that does matter too. Okay, when I look at the F1 scores for the unlabeled brackets, did we find all the brackets that were not the, unlabeled brackets, then well, to the left, we were doing really very well. And Menno van Zanden's system was doing better than Comino on a number of tasks towards the sort of the third part of the table. Okay, so now let's get to the natural language experiments, because I'm sure that was very nice for the grammatical inference community. When I go there and I show them that, they're very happy because we were doing better than, than state of the art. But what happens when we're trying to work on the data from natural language processing? So we did go for Wall Street Journal. We had to make some modifications. The first one was that we didn't really work on unsupervised parsing, because instead of working on the sentences and on the strings, we worked on the part of speech tagged sentences. So we did have use of the part of speech. Second thing is that time efficiency was going to be an issue. So whereas in the previous thing we could try for different merges with different more exhaustive strategies, here we went for greedy merging, meaning as soon as we found a merge that was okay, we actually did it. And then we also changed slightly the distance function also for specific reasons due to this corpus. So I'm not going to come out with the results. I'm going to come out with a number of things, a number of considerations. The first consideration was, would it be a good idea actually to do what we're doing? I mean, is this type of grammar so restrictive that we're not going to get anywhere? Right? Have we put too many restrictions with these strongly contextual? I mean, strongly means strongly. So go with strongly contextual grammars. And the answer was, well, okay, well, let's just do, suppose that we do phase one the way we did it. So we did all the merges. And then in phase two, instead of going for the minimum grammar, we somehow used the parse trees to rebuild from what we had the best possible grammar. And then we would find this line here, right, which would somehow say, well, there is a nice grammar to be found, but perhaps looking for the minimum wasn't the best idea we had. Okay, so there is a grammar of that nature to be found, which would be as good, or not quite as good, as the best possible of all grammars, which is in the last line. Okay, then there's a second idea, which was, okay, the idea here was we're trying to learn structure and at the same time to learn probabilities. So is there a context-free, a probabilistic context-free grammar to be found when we're looking at data there? And there's this sort of rather fun example where we're looking at the structure, which would be sort of noun phrase. And we're asking ourselves, does noun phrase exist? And if we look at the context of noun phrase to the right and to the left, are we going to be happy about what happens? And then, so what we're seeing here is that if we look at the event having an adjective in a noun phrase, it's going to be very much dependent on if you are before or after a verb. So if you take a noun phrase, I mean, probably people in natural language processing know this, but well, for us it came as a surprise, but if you were trying to look at this event and you're just thinking, okay, let's look at noun phrase, the fact that it's before, the fact that it's after the verb, the fact that it contains or doesn't contain an adjective is going to matter very much. You're going to have much more chances of having an adjective in a noun phrase after the verb rather than before. Okay, conclusion. Some goals achieved. We have understood a certain number of things about what PCFG learning was about. Learning in this sense, in the sense that we're not given the trees and we're not given a structure beforehand. We've got some nice results on the artificial data. Those results are showing that there is something there, that we've got some nice ideas. There's a third important point, which is solvers. Solvers are being used in learning for a number of tasks, and here's another task in which, well, adding a solver is helping us quite a bit. Lessons. Usually when you do learning through merging, you sort of do the reduction of the search space, and then you start doing merging. Here we've done the opposite. We're starting doing merging even when we've got too many things, and then we've reduced the search space, and that seemed to work. Second lesson, but isn't a lesson, it's more a question that we may raise, is going for a PCFG with the added question of wanting at the same time to have the right probabilities and having the right structure. Was it a good idea after all? I mean, perhaps for other tasks maybe, but here it certainly seemed a little bit too challenging. And that's basically one of the reviewers who said there may be a no free lunch theorem here, saying you can't do both at the same time. So that's probably where I'll stop. Thank you.
Thank you very much. That was a great talk. I was wondering if you could comment actually on the generalization to the synchronous grammars, so where you're generating two languages at the same time, your approach, and in particular in the practical setting of, say, generalizing it and yet constraining it to, say, word alignments, for example, in machine translation.
So I can't comment because I haven't tried, but I mean, certainly it would be nice and challenging. But I haven't got more comments than the fact that I don't know, if anything, apart from the fact that you were telling me that there was a nice paper on those grammars tomorrow.
Yeah, but maybe...
Not with these techniques.
Following up on this, the notion of congruence with synchronous grammar, so the relation would be with...
On both.
The relation would be with synchronous context. You have to simultaneously compare substrings by their...
Yeah. No, nice. You'd need to do quite a bit of maths because to be able to get... I mean, I was talking about cats and dogs, but the maths behind these congruential grammars are rather complicated. They lead to other things called NTS grammars, which have been around in the mathematics for a while. And so the maths need to be done, but I mean, yes, I agree. You'd be looking at context in both cases, on both sides.
Hi, thanks for the talk. Can you comment if you see some fundamental reason why it's difficult to learn a grammar that can do both parsing and language modeling? I mean, to get the right probability over strings and also the right trees.
Okay. So it's not that it's, well, A, it's difficult to learn, so learning where probabilistic context-free grammars is a difficult task. But it's more like, is it what, can the same model at the same time the structure and the probabilities? It's clear that having a context-free grammar is a very nice object for parsing, so we're very happy to have it. It's also clear that we like having probabilities to do language modeling, but once you've put the probabilities on a context-free grammar, strange things appear. I mean, you're starting to suggest that those structures really exist, you know, that sort of that you're capable of using, for example, to generate new strings. And so if you try to use the best possible probabilistic context-free grammar to generate new strings, you'd clearly be surprised by what the result is, for semantic reasons, but other reasons also, like the distributions just wouldn't match.
Yeah, you were saying that maybe finding the smallest grammar is not a good idea, like in terms of using the MinSat solver. So is there an alternative, like could you use other solvers out of the box, or if you want to look for something that's kind of a regularized minimal grammar, you would need to come up with your own solver?
So two questions for that. One is a great suggestion by one of the reviewers saying that he thought it was silly to, well, he didn't say silly, he thought maybe you could do better than separate stage 2 from stage 3, and that you could probably use, you know, at the same time that you're actually minimizing, you're at the same time trying to compute the best probability. So you could do the two tasks at the same time rather than separately. So that's the first answer. Second thing is, in the solver, you can probably add in a certain number of extra constraints. So it's not just the minimum in the number of rules or the number of non-terminals. You want to add some other things. You want to put in some weights in order to be able to do that. So we've tried a little bit, but not enough to get anywhere.
Your natural language experiments at the end, were they an upper bound or they were actual sort of F1 scores? I wasn't really clear from that.
Upper bounds, no. I don't dare, we actually decided that for our paper to be accepted, we wouldn't put our own scores in.
So what were they?
Oh no, they were in the 40s or something like that. I mean, they were really bad. They were very disappointing.
Actually, I have a question. So your method is based on clustering substrings with respect to the equivalence of their context. And so that gives, the first step does this kind of clustering. So I'm wondering if you can use any sort of clustering algorithm that clusters substrings based on similarity of context. In NLP, there's a very famous algorithm, the Brown clustering algorithm, that clusters words with some using some notion of likelihood criteria to merge them.
Yeah.
So I'm wondering if an extension of the Brown clustering algorithms, where instead of just clustering words, you cluster substrings, if that's feasible computationally, could be plugged here.
Okay, sounds nice. The thing that matters here is that there's some dependencies. The fact that, for example, in red, you've put AB and AABB in the same class is going to oblige you a little bit further for the grammar to actually be consistent, for you to have a grammar, to actually put AAB and AAABB. So rule 3, in a way, induces things over rule 6. So you've got a certain number of constraints there that are due to the nature of the grammar you need to have. So if you're able to use other clusters and still land on your feet, have a grammar at the end, why not?
Further questions? Okay, so thank you very much. Let's thank the speaker.